Hello, I'm Konstantinos Tovletoglou from Queen's University Belfast, and I will be presenting HaRMony, Heterogeneous-Reliability Memory and Quality of Service Aware Energy Management on Virtualized Servers. One of the major contributors in energy consumption of modern computing devices is the DRAM, which can reach up to 54% of the total power consumption in servers. Furthermore, the modern workloads are demanding exponentially more memory capacity, higher density and increased bandwidth, altogether at a lower power consumption. So far, the scaling of the transistor and the feature size of the DRAM cell have proved sufficient to cover those requirements for the required performance and energy improvement of the memory. However, memory is rendered even more susceptible to errors at lower nanometer technologies. To retain the same reliability, manufacturers adopt pessimistic guardbands. This approach hurts both the performance and the energy consumption of the memories. Those guardbands are selected based on the worst-case condition that the chip can experience, which may rarely occur in normal operation. Furthermore, by applying the same guardbands across all the memory chips, they ignore the fact that there can be a great variability of the reliability of each device. Another technique to ensure high levels of reliability is employing error correction codes, which are worsening the performance and energy consumption of the system. Finally, we come to the realization that trying to mitigate every error will be expensive in future technologies, so it may be wise to apply the aforementioned techniques only for parts of data, as it has been shown that some application data may be resilient to errors or that some application flow criticality could be restarted if there was an error. The guardbands that are introduced in DRAMs are the circuit parameters such as the high operating supply voltages and the frequent refresh operations. For example, the required refresh operation is degrading the performance as the memory is unavailable while it is refreshing. So there is a 4% performance overhead in current DRAM densities and up to 20% in future 64 gigabit DRAM chips. Furthermore, the power overhead of refresh is paid even in the case that the memory is idle. Currently, around 9% of the DRAM power is consumed by refresh, while in future densities it will reach up to 31%. In terms of error correction codes, it is typical in server to utilize SecDet ECC, which requires 12.5% extra memory to be able to correct single-bit errors. We want to relax the DRAM circuit parameters to reduce the energy consumption of the memory. By doing so, we affect the reliability of the system as the memory will be more susceptible to errors. In our approach, we want to exploit the fact that some applications can tolerate error in their data structures as the resilient properties of their algorithms may mask the errors. Those data structures are suitable for the memory operating under relaxed parameters. However, to ensure the reliable operation of the system, we need also to protect the critical data that need to be error-free, such as the operating system data and application data that will lead to a crash if there is an error. To accommodate for such application and enable the exploration of relaxed parameters and error resiliency on real server, we introduce HaRMony, a heterogeneous reliability memory framework which enables us to separate application data based on their criticality and tolerance to errors. With HaRMony, we can allocate data either on a reliable memory domain that is operating under the nominal DRAM circuit parameters or on a variably reliable memory domain that we can exploit better energy efficiency by relaxing the DRAM parameters. We faced quite a few challenges trying to implement such a framework on a real system. Initially, we found out that we have to disable the hardware-based interleaving. This results in an enormous performance overhead, and we propose a software-based interleaving scheme to mitigate the overhead. As with every new framework, HaRMony may be difficult to adopt in the already existing modern software stacks. So, we implement an intuitive interface to expose the capabilities of heterogeneous reliability memory in all the levels of the software stack, from low level for bare metal execution of workloads to high level for allocation of whole virtual machine in variably reliable memory. To ensure the seamless operation of the server on cloud deployments, we introduce a transparent policy to manage the heterogeneous reliability memory for cloud users. To do so, we propose a governor that is selecting the optimum DRAM parameters to maximize the energy savings while respecting quality of service constraints of the user. Furthermore, we give the option for the advanced user to manage manually the trade-off between energy and quality of service. Finally, there is a need to evaluate HaRMony on a system under real environmental conditions such as temperature and across a range of workloads. We found that hardware-based interleaving poses an issue trying to implement HaRMony on top of a real server. The hardware-based interleaving is utilized in most servers so that consecutive accesses are spread in multiple memory channels, exploiting them in parallel and improving the performance of the memory subsystem. However, the challenge arises when critical data must be stored in reliable memory, but are spread in all memory channels, including those operating under relaxed parameters. Therefore, the hardware-based memory interleaving must be disabled. However, disabling of the interleaving results in not utilizing efficiently the bandwidth of all the memory channels. We have done experiments showing that the performance overhead can reach up to 228%. In order to face the first challenge, we expose the configuration of the hardware-based interleaving at boot time and disable it for allowing allocation in a single memory channel. Allocations that require data to be stored reliably can target memory controllers that are operating under nominal parameters. To mitigate the incurred performance overhead, we propose a software-based interleaving scheme for HaRMony. We developed this capability so that the allocation can target multiple memory controllers and spread the allocated memory across all the channels. This way, we are exploiting the available memory bandwidth in parallel. To enable the use of heterogeneous reliability memory, we expose the introduced reliability domain to the users through the NUMA interface of Linux OS. Each memory channel corresponds to a NUMA memory domain, which can be assigned to either the reliable or the variably reliable memory domain. The default allocations, such as malloc, are always targeting the reliable memory domain, so the operating system and the application that are not manually configured to target any reliability domain will be stored in error-free memory. The programmer can control the reliability domain of a whole application by invoking the NUMACTL command. Also, the source code of an application can be modified to replace the default allocation function with corresponding NUMA function. This way, resilient data structures can be allocated on variably reliable memory. The same interfaces have been extended to enable selecting multiple memory channels and utilizing the software-based interleaving between the memory channels of the same reliability domain. To extend the interface for virtualized execution, we introduced two policies. The first policy is transparently exploiting the capabilities of the heterogeneous reliability memory inside the virtual machine. The only requirement for the cloud user is to provide a quality of service threshold that is willing to tolerate. The virtual machine is further protected by a checkpoint and restart mechanism. The checkpoint interval is based on the expected mean time between failure caused by the relaxation of the parameters. We develop a governor that scales the DRAM parameters dynamically to decrease the power consumption while respecting the quality of service requested by the user. For the second policy, we allow the cloud user to make the selection of the reliability domain for each allocation. We extend the interface of the bare metal system to the virtual machine hypervisor for allowing to allocate variably reliable memory inside the virtual machines. The user has access to a new interface that can be used in the virtual machine that can control the DRAM parameters. Our framework is implemented on a commodity server, the XGen2 by Applied Micro, which provides 4 memory controllers which for our experiments are equipped with 4 8GB DDR3 DIMMs. Our modification of the NUMA interface are realized on the Linux kernel 4.11. To manage the virtualized workloads, we are using the QEMU hypervisor version 3.0 running with KVM capabilities. As the server has 4 memory controllers, we configure the reliable memory domain to consist of 1 memory controller, while the variably reliable memory domain can have 2 configurations, either the 3 memory controllers operating under relaxed parameter or across all 4 memory controllers. The specific server enables relaxing the refresh rate up to 35 times, which can be controlled for each memory controller separately, and lowering the voltage by 5% for each pair of memory controllers. In order to stress the system, we have developed a thermal testbed for the DDR3 DIMMs that allow us to control the temperature into ranges that uncorrectable errors are introduced in the execution of the applications. We have evaluated HaRMony running workloads natively with the spec CPU 2006 benchmark suite, which represent a great variety of typical workloads. For virtualized workloads, we have divided the virtual machines into two groups. The first one, with workloads that are sensible to errors and require you to restart the VM in case of an error, and the second, with workloads that are error resilient and execution continues even when errors occur. For the first quality of service management policy, we are using all the virtual machines from both categories, while we evaluate the second policy with the error resilient workloads that have their allocation modified to allow the resilient data on the variably reliable memory domain. Moving on to the experimental results, we start with the native execution of the spec CPU 2006 benchmark. In this graph, you can see the performance overhead introduced by the Heterogeneous-Reliability memory framework with disabled hardware-based interleaving and HaRMony with two configurations. Disabling of the hardware-based interleaving incurs a considerable performance overhead, around 30% on average, which can reach up to 228% for the LBM benchmark. HaRMony can mitigate the biggest part of the overhead, reducing it down to 1.1% and 5.4% on average for HaRMony interleaving across 4 memory controllers and 3 memory controllers respectively. Both the non-interleaved and HaRMony achieve similar DRAM power reduction, around 20% compared to the system with nominal parameters. The fact that the DRAM power reduction in the system with disabled interleaving is higher can be explained from the reduced performance and the memory is not accessed as frequently. It is interesting that the most power-hungry applications have also the highest decrease in power consumption. We observe that the total energy without any mitigation is 17.2% higher than with the system with the nominal parameters. This indicates that any implementation of heterogeneous reliability memory that does not mitigate the performance overhead of the interleaving will not be energy efficient. HaRMony with 3 memory controllers interleaved barely has any energy savings. The average 0.6% reduced energy consumption shows that HaRMony with 3 memory controllers interleaved may be suitable only for a few of the benchmark. This makes it clear that if the software interleaving is not optimally configured, energy may not be reduced. HaRMony with 4 memory controllers interleaved can save 8.6% across the spec CPU 2006 benchmark, and for all the benchmark we observe some degree of energy savings. Moving on to the virtualized workloads, we are using the Young and Daly formula to derive the optimal checkpoint interval. However, as the formula is for a constant mean time between failures, we have extended it to be based on varying mean time between failures. As relaxed DRAM parameters and increased temperature will result in more frequent crashes. We have measured on the server the duration of the checkpointing of each VM and the duration it takes to recover from a crash. We have calculated the lowest mean time between failures that the system can experience so that the user requested quality of service is not violated and the optimal checkpoint interval for each virtual machine. Here you see an example of HaRMony with the quality of service aware governor that dynamically adjusts the refresh rate of the system. The governor considers the availability of the system and the DIMM temperature to select a refresh rate for the maximal power savings while respecting the quality of service requested by the user. On the left axis, with the orange line, we show the availability of the virtual machine and the minimum quality of service requested by the user using a solid horizontal red line. The right axis with the blue line shows the refresh rate that the governor has selected. The second right axis with the green line shows the temperature of the DIMMs. The lightly colored vertical lines indicate the timestamp when the virtual machine is checkpointing, while the dark lines indicate the moment when the virtual machine detected an uncorrectable error and had to recover to a previous checkpoint. As expected, we see that the governor relaxes the refresh as long as the user constraints are met. Initially, quality of service of the virtual machine starts at 100%, and then it decreases since each checkpoint makes the system unavailable for a duration. Whenever the virtual machine crashes and needs to be restarted, the quality of service may be lower than the one requested. In this case, the governor quickly reduces the refresh rate to a more nominal state. We see that the virtual machine has crashed at the 16th hour. However, quality of service has only momentarily been lower than the one requested. As a result, the relaxed refresh rate has not changed significantly. Furthermore, we observe that the governor limits the relaxation of the refresh rate since the DRAM temperatures has greatly increased. While the temperature is lowering, the maximum refresh rate allowed is increasing. For the virtualized workloads, under the first policy, we observe an average performance overhead of 12.6% for the system with disabled interleaving. HaRMony reduces the performance overhead down to 6.1% and 6.7% when 4 and 3 memory controllers are interleaved respectively. The performance impact of disabling the interleaving follows the same trend as the previous results of the workloads running natively. However, it seems that the impact is smaller. Similar to the native execution, virtualized workloads have increased system energy consumption if there are no mitigation of the performance overhead. Eventually, HaRMony can save 5.9 and 8.4% of the system energy for the virtualized workload for 4 and 3 memory controllers interleaved. Compared to the native execution of the workloads, we observe that interleaving 3 memory controllers is more energy efficient for the specific workloads. To conclude, in this work, we have implemented HaRMony, a heterogeneous-reliability memory framework on a real server in which we overcome the challenges of realizing such framework. We have introduced a software-based interleaving scheme which reduces the performance overhead, which can reach as high as 228% down to 1.1%. We have provided an easy-to-use interface to exploit the capabilities of HaRMony for bare metal and virtualized execution of workloads. We have proposed 2 policies to manage the trade-offs between energy and quality of service. The first policy dynamically controls the DRAM circuit parameters through a quality of service aware governor while meeting the user's requested quality of service. The second policy enables users to exploit the inherent application error resiliency by allowing to allocate data instructions on variably reliable memory. We have achieved 8.6% system energy saving on average for non-virtualized workloads and 8.4% for virtualized workloads, ensuring the seamless operation of the server even under extreme temperatures. I would like to thank the Horizon 2020 project Uniserver and Obricon and all of you for watching this presentation. Please contact us if you have any questions.